Next talk, Stefan Mar, how to get a JIT compiler for free.
Yeah, so I'm going to talk a bit about virtual machines, or actually just simple interpreters instead of just-in-time compilers. Because one of the big problems we have is that way too few people actually work on the virtual machines they use. So in open source projects in general, typically you have way too few contributors. But then typically you have only one person, maybe, well, I think there are at least two people in the room who have been touching virtual machines. But there are way too few people actually looking into how to get all that kind of stuff fast and how to make it work on all kind of platforms. So I've been looking a bit into that and what we can do about it. And I've been looking into that using a very simple Smalltalk, because it's easy to implement and you can implement it in all kinds of different variations. And that's actually a Smalltalk they have been using for teaching. So here down below you see a couple of the universities who have used that. And the main design constraints here were to have something really simple for teaching, to have something that's really showing the concepts in the ideal textbook way, which typically means it's not very fast. And then we have a couple of interpreters implementing that. Actually, we have all kinds of different implementations and all kinds of different programming languages by now. So, but as I said, one of the main drawbacks is the whole thing is pretty damn slow. But it's easy to teach, as you can see here, on two of pretty common object-oriented benchmarks originating from the Smalltalk world. Richards, well, actually Richards, I don't think so, but at least doesn't do. But they have been used for Smalltalk, JVMs, JavaScript, and PyPy, I think. And you see like 500x slower or 70x slower than Java. Java is, of course, well-tuned, and hundreds of many years went into making Java fast. And our simple interpreter, of course, can't keep up with that. So, but what we want is, of course, something different. We want a simple interpreter that perhaps everybody of the community can change in order to make certain things better. It has to be a simple implementation, it has to be conceptually clear to really lower the burden. For instance, in Smalltalk you have your primitives. If you want people to be able to add new ones or adapt them or basically replace the mechanism by something like native boost, then you need people that actually can change the virtual machine implementation. So we want all of that. But of course, we also want kind of that, so at least that region, the same order of magnitude would be nice. So the green, now unfortunately cut off, is actually the virtual machine here. So on Delta Blue, barely 20% slower, and on Richards, it's 6 times, 7 times slower. But at least not the 500x. So that's where we want to go. And ideally with that kind of very simple interpreter. So how do we get there? At the moment, just-in-time compilers, as I said, it's really just a few people doing that. So often it's just arcane magic. So there's one person in the team or in the community doing that. We see that in the Coq virtual machine, that's basically Elliot Miranda. The Lua people have the guy behind LuaJIT, and I think there are other communities like Racket where it's very similar. And then the other option is basically to, well, have a big office or infrastructure for engineers, the Java way, the IBM, the Google way, the same way they built Dart, for instance. Just have the engineering resources to do that. So, but none of those solutions is really sufficient. So let's look a bit into what science came up with recently. And, well, it's really unfortunate. Down below here, you see actually the references. But, well, the slides will be online later, so you can look that up. But there are two interesting options. So you might have heard of PyPy. They use infrastructure they nowadays call RPython. They have a meta tracing just-in-time compiler, which is a very interesting approach. And then very recently, Oracle Labs open sourced a project called Truffle, and they have self-optimizing interpreters based on partial evaluation and the whole tool chain based on Graal, just-in-time compiler tool chain to do those kind of things. And I'm going to briefly look into both. So what's SUM? Just to give you a brief impression, that's a simple Smalltalk, has been developed, I think, around 2000, somewhere in Aarhus at the university for teaching. A text-based syntax to make it really simple to build the very first interpreter. And as you can see here, object doesn't have a superclass, has a primitive to get the class object of an object, has a pointer equality primitive and other stuff. Integer, for instance, has addition, subtraction, and so on. And then, of course, we have things like booleans in the system, and that's very much the Smalltalk tradition. You really have a polymorphic method that's then using the standard if true, if false to implement that. And if you look at the true class, you see if true is then actually implemented as you would implement it. Very simple, straightforward, in an ideal Smalltalk implementation by just evaluating the block, and in the false case, just returning nil. So, a very straightforward, simple Smalltalk, typically based on an interpreter. And to explain how that works, let's look at the factorial. So I don't have a shopping cart. My running example is a factorial, to keep it even a little bit more simple. Just to explain, I think everybody can read that here, I suppose. Can anybody not read Smalltalk? Okay, good. Very good. So Smalltalk, the first thing you notice is those two things here. That's actually one method invocation, or in Smalltalk a message sent. And the receiver, so the object on which you invoke that, is here the evaluation result of that pair of parentheses. So we have the simple comparison whether n is 0 or not. And if that's true, then we evaluate the block, which is a closure, and return just 1 as result. Otherwise, we evaluate that block, and we'll just recursively evaluate the factorial. So nothing too fancy. Maybe if you can't read Smalltalk, maybe you're better with reading something like bytecodes.
Oh yes, thank you. That helps.
That's I don't know how whether I can shrink or move my slides somehow. But I have to try to change the resolution once more. Is it going to be a big problem with the recording?
Maybe just try. We'll see.
Well, let's do it. Can I do the animations here? No, probably not.
Nope.
That kills it?
Yeah, it breaks.
It breaks it up. So,
Well, then I will reset it after that slide, I think. Anyway, so now we at least see the slide. So the idea is, if you want to implement an interpreter, the classic thing to do is to build a set of bytecodes and then have a stack machine to interpret those bytecodes. So if you actually compile the factorial to a very, very simple bytecode set, so in a simple thing in Smalltalk, I think we need something like 16 operations. Some of them are like pushing arguments from the function, pushing constants, doing the actual send, and then special things like pushing a block and returning from the function. So if you imagine, if you think how that could be executed, here our example code, that's actually the first thing we do. If we invoke that method factorial with 4, we push the 4 on the stack. And then the second operation is the 0. And thereby we can now actually do the message sent here for the comparison. And that will, on our stack here, so if we don't look into the details of how that comparison works, yield the result false. So very simple stack operation. We use the stack to basically build up first the arguments for the message sent and then have the result on the stack. So and afterwards you can imagine very much the same to prepare that send. Here we push the 2 blocks onto the stack and you send the result, and eventually either a 1, which was a result of that block, or the actual factorial will end up on the top of stack here, and that's something we can return. Okay, let's try to make the recorder happy again. No. Okay, better? Yeah.
Yes.
Okay. So I basically showed you now how to interpret such a bytecode sequence based on the factorial program. The implementation of that is also more or less straightforward. So we have here in a kind of Python syntax, because that's actually more or less the RPython interpreter I implemented. And you see here, yeah, the interpret method. You get the message you want to interpret. You have a frame, that's basically the stack I showed you on the side. And what we then do, we basically loop over all the bytecodes as long as we have bytecodes, or actually as long as there is a return bytecode. So we start then here with the bytecode, and then typically that's a very standard thing. We switch over the bytecode and jump to the right thing to do. Yeah, well, that's very classic. That's not very fast, and that's actually what more or less yielded the thing with 500 times slower than Java. So now here comes the meta tracing of Python, or not Python, RPython into play. That's what the PyPy people also use to implement their really fast Python implementation. So the only difference that comes actually in here is that we tell basically the RPython infrastructure that that specific bytecode loop here can be, yeah, the start of how do I phrase it? Yeah, normally hot loops, or that's an interesting point to start to generate native code. So if the RPython notice at such a point, such a merge point for the just-in-time compiler, that a certain loop has been executed again and again, then it can assume, okay, now we can actually spend a bit of time to compile that into really fast native code and generate our, do all our optimizations to generate that code. That's not always useful, so that's why we need to do that explicitly, tell about that. But that's more or less what we actually need to do. So what does the tracing then actually mean? Well, let's look at our factorial example again. So what happened now is we execute, we start executing that method, and we take basically the first bytecode. So what that means, if we are now in the tracing mode, we actually ignore things like jumps and branches and so on, and instead really just record the important actions and certain assumptions. And I left also out assumptions, so really just recording, reading and writing of fields, because that's what's really interesting. So what happens is we actually need to go to the method object, get the bytecodes out, we remember that in a variable, and then we go to the index we had and read out the bytecode and the arguments. And then, as I said, we are not really recording any kind of jumps, which has now happened here at the switch, but we really just record the actions. But we know now that actually the first bytecode in that method was a push argument bytecode. So what now happens with the push argument bytecode is exactly that fragment. And as you also might notice, we actually didn't note down any kind of method invocation, because it's all not really relevant. We really just want to know what were the concrete actions performed. And then here again, we start with a frame get argument. So we go to the frame, you go to the arguments array, get that arguments value out there, and basically note all those operations down. Then we want to perform the push itself. So we need to go to the frame. We get the stack pointer out, we increase the stack pointer, we write the stack pointer back, and then we get the stack out of the frame, set the specific position at the stack with a value, and now we actually pushed the argument. And if you now continue and imagine, okay, well, first we of course need to increase the bytecode index, which we don't see on that slide, but then we execute the next bytecode. And then it happens all over again. At least very similar sequence of operations. And there you might already see, actually we do quite a lot of stuff again and again. And that's where actually the tracing, and the meta tracing in particular, has a lot of benefits here. So if we, for instance, look a bit closer at that trace, and we see here at the beginning, just accessing that bytecode array, we do at least twice. And at least for every bytecode once. So now I have 2 bytecodes only executed, but methods or typical execution traces will be much, much longer. So and then the other thing is here, access to the stack array, which should be happening somewhere down here as well. And we can really just remove those operations because we put that here in a temporary variable already, and that's really the same value. And a simple optimizer can see that. And then we see here the same kind of stuff, pattern again, increasing the stack pointer. We can also, ideally optimize it out. And the people around the RPython project did the necessary research, and they actually showed that about 90% of the operations in such a trace can be, on average, eliminated. So I think that was between 40 and 97%, depending on the kind of benchmark they run, that you really eliminate all those operations, and then you can ideally really reach the peak performance for a specific problem by using that kind of tracing compilation. And I think the success of the PyPy project shows that very much. So, but that's only one approach to implement interpreters. And I had to explain you a stack machine and how to do all that, and that was already a bit hairy and not very straightforward, and it was also not very clear how to compile actually that code to a bytecode set, because it's a linear representation of something which, if you would use a simple parser, probably would more look like a tree. So if you parse that function, then we have that if true, if false as the main message sent basically, and the receiver on the left, and then the arguments, the first block and the second block in a tree structure. And actually implementing interpreter for that is pretty straightforward as well, maybe even more simple. So if we imagine we had here such literals, so they're really in the code as a constant given, and we can just implement that on those AST nodes if you want with an execution set, and really just return the value. And very similar for reading a variable. So if you compile that code, at least in Smalltalk, it's very simple to know at which position that variable should be. So we can just remember a certain index or a name for the variable, and then just really read the variable in. Then we interpret that AST and execute that execute method. So that's really very straightforward. It's, I would say, even simpler than that stack machine. And then we can even look at something more complex here, a message send. What's a message send doing? You have a receiver and maybe an argument, right? So if you have a binary message send, what do we do? Well, we simply execute the receiver expression, because the receiver is going to know what actually he has to do to return us a value. And the same with the argument expression, you also just return that. And here I didn't have to encode the stack explicitly. I can actually just reuse the stack of my implementation language and just have in my code here receiver argument variable and so on. And don't have to think about stack balance and what do I have to push first, what do I have to push later, and so on. So implementing that kind of interpreter seems to be much more natural. And then you can go to the receiver, get its class, do a lookup with a selector, and then you get a message that needs to be invoked, and we just return the result here. So, at least from my perspective, that seems to be much more natural and simple way to implement an interpreter. And that's where truffle comes in. So the Oracle people here actually came up with an idea to optimize those kind of AST-based interpreters by, at runtime, specializing those ASTs based on what actual values were observed. So taking that message sent, one of the most important things here to specialize for is actually the lookup, the receiver, and the method we eventually want to execute. So especially in Smalltalk, where you have to walk dynamically the inheritance chain to find the method or the method that corresponds to the selector, that's a pretty expensive 5 minutes, yeah. So I'm only sketching how that works here, especially with time constraint. The idea is really you have that AST tree here, and that's then specialized to an execution tree that has very specific nodes in there that really does just perform the minimal operations or go to a fallback node. So one thing you can see here indicated with colors, that variable read, for instance, became read an integer to avoid overhead of boxing on a JVM, for instance. And that generic binary send converted into a cache send, there's a couple of extra nodes. So the class check is an extra node, and then here's actually an inlineable send, because often you get much better performance if you inline a method, because then you can specialize it in the calling context. And well, because sometimes you do really have polymorphic message sends, that one single cached node might not be enough. So you have actually a chain, and so you can have something like a polymorphic inline cache, which is, customly, tricky to implement in a virtual machine, but very important, especially for Smalltalks. And here it's really a tree structure, or well, at least, I think it's still a tree, and of nodes, and you have a very high-level representation of all of that. And that builds very nice interpreters, and they get actually pretty fast. And how fast? Well, is it just a toy, or is it really what we want? That's the results. So what I have to say at the moment, the RPython version, so the stuff running on top of RPython with the meta tracing, I had the support of Carl Friedrich Bolz, one of the PyPy guys, who actually made it that fast. And as you can see here, we are barely 30% slower than Java. If you remember, the cockroach machine was 20% slower than Java, so we are still a little bit behind. So on Richards, we are within a factor 10, which is more or less our goal, so just barely slower as Coq as well. The troublesome here, unfortunately, still stumble into some bugs here and there. Just recently, the Oracle guys actually thankfully fixed a couple of things for me. Well, non-local returns, one of the most important features in Smalltalk for the control structures, wasn't supported all that well, and of course a lot of recompilation problems. So I haven't been able to tune that as much yet, and it's also much more to the implementer here than to the black box toolchain. But I think we can get where we want. So now, as a conclusion, the question was, can we have maintainable design, simple implementations, and clarity to basically reach more people actually maintaining interpreters and virtual machines? And I think yes, that's totally possible. So the nice techniques they have with either the meta tracing or the self-optimizing interpreters, that's a good foundation for that stuff. When it comes to performance, well, I would say at least it's plausible, but it still has to be seen exactly. But I think it's also possible with both things to reach that kind of performance. And well, where is that leading? I hope that's leading to me investing a bit of time to push those kind of ideas into Mate and maybe the cockroach machine in Siesterberg together with the Faro people. Yeah, so that's for the future. So there is nothing happening yet. So are there any questions?
Maybe the same question. I'm doing a bachelor test, final test, what do you call it?
A thesis or?
Thesis, yeah. And the subject of my thesis is make your own programming language. That programming language, maybe an interpreter or
a simple compiler
or anything, but it has to be really designed into a ERP system, an existing ERP system. Are there any tips you can give me for my thesis?
Well, it will probably depend on the ERP system. But if you really just want to implement a very simple interpreter for instance, domain-specific language,
it's script. It has to be a scripting language to actually catch errors from printers, from mail. So if a printer gets an error, then the client has to be able to write a script to actually say, yeah, those persons need to be mailed and that mail need to be sent.
Well, depending a bit on what kind of infrastructure we are talking about. So the truffle stuff with the AST interpreters, which I would think is a very nice and simple idea that can also be applied in different contexts. That runs on Java. So you could just go to their open source page and look a bit around. There's not a lot of documentation, which is a bit of a problem, but there's like a simple language implementation which shows a couple of concepts. So you can try to look that up. So it's under the Jar umbrella of the OpenJDK. And otherwise, you can also easily implement on top of something like Faro or Blue Smalltalk a simple AST interpreter. That's very straightforward. So just grab your textbook and go devise a grammar, implement an AST interpreter. So I don't know what to advise more. So those techniques we have here are ready for performance, and I don't know whether that's a critical point in your thesis. If so, then
it's more simplicity of syntax and not about performance, because the clients aren't necessarily programmers. It's not
then I would.
So I believe ERP systems performance is kind of like important.
Due to time constraints, I would like you to take it offline and talk later to the students. Okay. Thank you very much.
Ja, Sie sind ja auf 2024 schnellzeitigen Folien, also ich weiß nicht, ob Sie da mal gucken muss. Power. Yes, power. Ja, das ist von
if you have white slides, it's good to not stand in front of the slides because the video is not going to be anything.
It's less natural.
let's see.
Sound okay?
Oh, it's a bit cut off, but I guess it will work.
Yeah.
No, stay.
Of course, they meet with the 504.
Yeah, well, that's
Why you do
close somewhere.
Yes, please get a bit closer to the speakers.
Yeah. Okay.